When using a trapezium rule, I always just like to write out the general form. So if we're using four strips and we're integrating between a and b of some function, then we get a half h y0 plus y4 plus two lots of y1 plus y2 plus y3. So let's set up a little table. In this case, h is going to be 1 minus 0 over 4, so it's going to be a quarter. And then we've got our different x values and our different y values. So 0, a quarter, a half, 3/4, and 1. Okay, put in 0. 16 to the 0 is just 1. 16 to the quarter is actually the fourth root of 16. That's going to be 2. Square root of 16, which is 16 to the half, is 4. To the 3/4, we cube when it's to a quarter, so we get 8, and then finally we get 16. So nice integer values here, even though we've got an exponential. And that means that the integral is going to be approximately equal to a half times a quarter, and then 1 plus 16, got the two values either side, plus 2 lots of 2 plus 4 plus 8. That will become an 8 multiplied by 17 plus, now this is 6 plus 8, so 14 plus 28, giving us an answer of what will be 38 plus 7, so 45 over 8. We're asked in part B to then do a very similar thing, but with n strips. So going to go straight into it. 1, 0, 16 to the x dx. That is going to be, again, we've got a half times h. But this time I've got my y0 then plus yn plus two lots of all the rest of them. Okay, h this time is going to be 1 minus 0 over my n, so 1 over n. And then my integral, sorry, this should be approximately, is going to be 1 over 2n. And then y0 is 16 to the 0, which is just 1. 16 to the 1 is 16 again. Okay, and then what happens? Well, last time we went up in quarters every time. It was 16 to the quarter, 16 to the 2/4, 16 to the 3/4, because we're just adding an extra quarter every time. This time we're going to get two lots of 16 to the 1 over n plus 16 to the 2 over n, and so on, up to 16 to the n minus 1 over n. That's what it's going to end up looking like. So if I bring this together, then I could I could write it as 1 over 2n, 17 plus 2. There's a bit more space now just to write it again, but basically this is going to be our answer. We've got a geometric series actually. It's good to spot that at this point. When I did it, I actually brought that is, by the way, fine as an answer. I actually brought the half inside and wrote it as 17 over 2, because I just kind of like to get rid of this 2. that is it. This here with n trapezia is going to be approximately equal to this. Part C then says, hence showed the actual exact integral can be written as shown. So we need to bring this limit n approaches infinity in, which actually naturally happens. As we use more and more strips, more and more trapezia, we are going to get closer and closer to the integral, and the limit as n tends to infinity is going to give us our exact answer. We can go straight for it. And the way I've written it is quite useful because I've already got the 1 over n there. And I basically got the same thing. I just don't have a 17 over 2. So I'm going to do this in 2 steps. I'm going to just first of all write out the same integral. Let me see how they left their brackets. They just used normal brackets. Right, now this is almost the final answer, except this is not a 1. But what I can do when you have limits is, well, first of all, I can just, that's 17 over 2, so it's 1 plus 15 over 2. So I can write it as the limit of 1 over n, and then times 17 over 2 plus the limit. See, when you're adding limits, so lim a plus b, you can actually find the limit a and add it to the limit b. I think this assumes that both limits exist separately and a few other things, but it's going to be fine here. I think we can just quote this result. So limit n approaches infinity of 1 over n, and then suddenly we get the 1 in there. And here's the thing, as n approaches infinity here, this is actually going to tend to 0. And so that gives us our answer. That's the trickiest bit in this question, realizing that we've got this we've got this extra term here, but it's going to tend to 0. So we can get rid of it. Now, actually, it's true that this one here would tend to 0 as well, but it's going to be useful to have the 1 in the next part, which is why they've made us leave it in. Okay, on to part D, where we're asked to use integration to determine the exact value of the integral 16 to the x dx from 1 to 0. Okay, you might have learned this result. If you haven't, then this is how you can do it. This is like a proof of where it comes from. We can write, you know what, let me just do it up here. We can write 16 to the x as e to the ln 16 to the x. See, e and ln are inverse operations, so you can just bring them both in. And the reason that you do this is that now we can write e to the ln 16 to the x as e to the x ln 16. And this is essentially in the form e to the kx. And when you integrate e to the kx, you just get 1 over k times e to the kx. So here, we're going to have the integral of, let's just put it in, 1, 0, e to the, now I'm going to actually write it at the front just to make it clear that it's this constant. So what we'll get actually is 1 over ln 16 of e to the same thing, which I'm now going to rewrite as 16 to the x. And you might have gone straight to this, to be fair. That's what I'm trying to kind of illustrate. You can do that. When you differentiate, you just times by ln 16 or ln a in general, if it's a to the x. If you're integrating, you divide by ln a, or in this case, ln 16. So then we get 16 to the 1 divided by ln 16 minus then it would be 1 over ln 16, giving a final answer of 15 over ln 16. Good. This takes us to the last part. We're asked to evaluate this limit, and we're told that it does exist. And we're given some guidance to use part C in our answer to D. So let me write down all of part C. We showed this, so now I can just quote it, and it will be equal to 15 over ln 16. Right. And then it was to find the limit of x tending to 0, 16 to the x minus 1 over x. Okay, so there's some similarities and differences between I've got 16 to the power of something, I've got a 1 over n, but here n is going to infinity and x is going to 0. Now, if you've never seen this before, it's going to be quite challenging for sure, and actually there's quite a good chance you wouldn't have, because in A level you don't tend to do a lot on limits. But what we're going to do at some point is, because n is approaching infinity, what we can do is do a substitution x equals 1 over n, because if n is then approaching infinity, x will approach 0. So let's have that in the back of our minds along the way. If you don't know that, then you might still realize that later on, because somehow we have to do something with this thing here. And the first thing to see is that this here is actually a geometric series. So 1 plus 16 to the 1 over n. Now also note that this is not an infinite geometric series, because we are taking the limit as n approaches infinity later on, but that's we are going to be divided by n as well, so it's not quite the same. So a is 1, the first term, r is 16 to the 1 over n. So the sum is a times 1 minus r to the n over 1 minus r, which becomes 1 times 1 minus 16 to the 1 over n all to the n, divided by 1 minus 16 to the 1 over n. These actually just cancel, giving us minus 15 over 1 minus 16 to the 1 over n. And I can times the top and bottom by minus 1 now to make it 15 over 16 to the 1 over n minus 1. The bottom is actually going to be negative, I think. No, or n is approaching infinity. Oh, I don't quite know, but anyway, look, it's fine here as it is. Okay, so where does that leave us? So I can forget about the integral now. So the limit as n approaches infinity of 1 over n times 15 over 16 to the 1 over n minus 1, because I've just replaced that geometric series by this answer. That is going to equal 15 over ln 16. Okay, and remember, we're trying to work out this. So it's actually at this point that I'm going to do that little substitution. Let x equal 1 over n. Therefore, the limit as x approaches 0 of x times 15 over 16 to the x minus 1 will equal 15 over ln 16. And that means if I swap everything around, because this limit exists, then 16, by the way, at this point I probably should have cancelled out the 15s, then the limits as 16 to the x minus 1 over x is going to equal ln 16. With this final step, I've just taken the reciprocal of what's on the inside here and on the inside here, because that must be true. If the two things are equal inside, I know I'm taking the limit, then it must be when I take the reciprocals that they're also equal. And that is actually our final answer. Ln 16 is the limit. Okay, that's quite awkward at the end. Well done.